are some assessments you write and think that's a great assessment until you are asked to make a video. So when we approach this one, right, we're supposed to give the order of A through J, and we'll do that, but that's not really the point here. It's not to be able to know the order. It's really to learn the chemical shifts. And the best way to learn the chemical shifts is to practice by assigning them. This question is not great if you have to grade it, because there are lots of answers that are going to be close enough to correct. So my apologies to your instructors for making them grade it. If you're putting this into a computer program like mastering where there's some variability, my apologies to you. So with that out of the way, let's go through and do this problem. And the way we'll do it is we'll just put an approximate chemical shift for each of the groups here. And so we'll start with HA. That's a carboxylic acid. That's gonna show up around 11. And I'm not gonna put the approximate sign here or the part per million because all of them are approximate. We're just kind of pointing out sort of the range without showing a range, just around 11. HB is a hydrogen attached to an alkene carbon, so we would expect that to show up maybe around 5.5 would be a good number for that. HC is going to be a hydrogen on a carbon that's attached to nitrogen. So nitrogen is not super electronegative, but it's a little bit. So maybe we'll say that that one is around 2.8 parts per million. And again, just to emphasize that when you're looking at spectra, you're going to get some variability. So I might call that 2.8. It might end up being around 2.5 or 3.4. This is a hypothetical molecule, so just be prepared for those slight variations, but you want to make sure that within a certain range, you're getting close. HD is a hydrogen on a carbon that's not directly attached to an electronegative atom, but the nitrogen is there. We'll say that one's around 1.1 parts per million. HE is attached to the nitrogen. So anytime you have a hydrogen on an electronegative atom that can participate in hydrogen bonding, we're going to get some variability. So this is the one place where we will actually give a range, because it literally can show up anywhere between 2 and 5 parts per million. We'll do that same thing with hydrogen attached to oxygen if we get to 1. HF is another hydrogen on carbon that's attached to the electronegative nitrogen. So we would expect it to be pretty similar to C, just to make it a little bit different. In this case, because it's also next to the benzene ring, we'll say that it's more around 3.2, let's say. Just to make it different. And a hydrogen on a carbon next to an aromatic ring will be shifted a little bit farther downfield. So 3.2 feels good for that. G is an acetylenic hydrogen, so a hydrogen on an sp hybridized carbon. That's going to be around 2.5, let's say. Really anywhere between 2 and 3 is where we might expect to see it. So around 2.5. H is a hydrogen on a carbon directly attached to an electronegative atom, an oxygen. Now, it's more electronegative. Oxygen is more electronegative than nitrogen. So if this earlier one, HC, was 2.8, we would expect with oxygen there being more electronegative to have that be a little bit more deshielded, farther downfield, higher chemical shift. So we'll say 3.4 for that. That brings us to I and J. I is another hydrogen on a carbon directly attached to a hydroxyl group. So it's going to be pretty similar to the one to H that was around 3.4. So we'll say, just to give a different number, we'll say that this one is 3.3. But again, if you called it 3.5, perfect. Be happy with that. J is a hydrogen attached to oxygen. This is another one of those that can hydrogen bond. And so that's going to give you a range of probably 2 to 6. The range is a little bit bigger for oxygen because oxygen, being more electronegative, is even better at hydrogen bonding. So we'll say that it's between 2 and 6 parts per million. Now, if you wanted to do the question and place these in an order, you can, but you can see all of these places where we have numbers that are close together. It's kind of hard to say what would be the specific order. So I'm not going to do that. I'm just going to give you those numbers and say those are the chemical shifts. And the more you practice using them and identify what the chemical shifts are and know what you're looking at in a spectrum, the better you'll be at assigning structure to spectra.